Alright, welcome back. This is Daniel, and in this video we're going to introduce the concept of generics in Scala, which is an incredibly powerful tool in the Scala type system arsenal. Cool, so let's create a new Scala application in the part2 OP package. So new Scala class, I'm going to call this generics. As always, make this an object and extends app. Alright. Now I'm going to switch to presentation mode so you can see more clearly. So you saw in the previous video that we implemented a very cute linked list for integers. The trouble with that is that it's very limited to integers. What if we wanted to create a string linked list instead? With the tools that we currently have, we wouldn't be able to do that, and we would need to duplicate the entire code and put in string instead of int. So collections are a powerful use case where we would want a collection that could store elements of a certain type. So the way that we do that in the Scala generics world would be to define a class mylist parameterized with a type A, like I wrote here. So the type A here in between square brackets denotes a generic type. And once you define that, you can use the type A inside the class definition. When you then later use this mylist type, you can just say val list of integers is a new mylist typed with int in between square brackets. So the type int in between square brackets will then replace the generic type A for this instance of list of integers. Of course, you can define a list of strings with mylist parameterized with a type string instead. So notice how this code instantly gets reusable for every single possible type that we can store inside our generic list. So this, what we defined here, class mylist parameterized with A, is called a generic class, and the type A here is the name of a type parameter. You can give it whatever name you want. You can also have multiple type parameters. For example, if I define a class called myMap, which maps keys and values, I can have two type parameters here in between square brackets. So in between square brackets key, that is one generic type, and value, also another generic type. You can have as many type parameters as you want. This also works for traits. So if, for example, I turn this mylist into a trait, this also works fine, although the trait cannot be instantiated here because, well, mylist is an abstract type. So I'm going to revert this to a class, but I just want you to know that traits can also be type parameterized like this. All right. Now, I want to talk about generic methods. So let's say I define a small companion object for the class mylist. So object mylist. Just so you know, objects cannot be type parameterized. And let's define a method here in the mylist companion object that, given a type parameter, would construct an empty mylist parameterized with that type. So the way that we write this is def, let's call this empty, and we'll put in a type parameter here. So this is the method called empty type parameterized with A. And this will return a mylist parameterized with A. So once you declare the type parameter here, you can later use it in the function definition. So just assume for now that this function doesn't actually do anything, doesn't return anything. So this thing will return nothing. What I wanted to show you is how you define a method signature type parameterized with a generic type parameter. So the object mylist, which is a companion for the class mylist defined above, has a generic method called empty, which takes in a type parameter A and returns a mylist of A. And you can use the type A here inside the function implementation. But right now we don't have a function implementation. I just wanted you to see how a generic method looks like. And of course, the way that you would use this method is, let's say, val empty list of, say, integers. So empty list of integers would be to say mylist, the object, dot empty with a type parameter int. And this will return a mylist of int. If you hover over empty list of integers, it will say generics dot mylist of int. Alright, so now we know how to define and use generic classes and traits, and how to define and use generic methods. Okay, so this was easy enough. What's hard is what comes after. Now that we know generics, there are some hard questions that we need to answer, and this is called the variance problem. Let's define a little class hierarchy with a class animal and two subclasses cat and dog. So class cat extends animal, and class dog extends animal, of course. All right, so a small class hierarchy. Now the good question is, if cat extends animal, does a list of cat also extend a list of animal? Now there are three possible answers to this question. The first answer is yes. List of cat extends list of animal. This behavior is called covariance. And the way that you declare a covariant list is to say class, let's call this covariant list. And in the type parameter here in between square brackets, you put in a little plus a. So plus a means that this is a covariant list. Now the way that you would use a covariant list is in the same style that you would use cats for animals. So in the same style that you would say val animal typed with the type animal equals new cat, the way that we did with the polymorphic type substitution earlier in this section, the same way would apply with an animal list. So we say animal list, which is a covariant list of animal. And instead of a covariant list of animal, I just put in a new covariant list of cat. And this would work well. Now an even harder question. Now, once I declare an animal list to be a covariant list of animal, and its actual value, I don't really care about it, can I actually add any animal to it? So if I say animal list dot add a new dog, would that be okay? That's not a trivial question, because animal list is defined to be a list of animals. So in theory, I should be able to add any animal, but adding a new dog to an animal list, which is in fact a list of cats, would actually pollute the list of animals here. So this is a hard question. This was the first option. Second option, let's count these. So 1, yes, list of cat extends list of animal. The second option is no. List of cats and list of animals are two separate things. So this would be an invariant list. This is called invariance. And the way that you would write a invariant list, so I'm defining an invariant list class here, simply specify the type parameter without any signs before or after it. So the mylist type that we defined at the beginning of the lecture is actually an invariant mylist. Invariant classes are each in its own world, and you cannot substitute one for another. So if I say val the invariant animal list, which is defined as an invariant list of animal, you cannot substitute that with a new invariant list of cat, or invariant list of anything else for that matter. So if you define something to be a list of animal in this case, you make sure you put in animal on the right hand side here, because otherwise the compiler will throw errors in your face. Now this option was very easy. The third option is very counterintuitive, and it's basically the opposite relationship. I'm going to call this hell no. And the relationship is called contravariance. Contravariant classes, I'm going to define a contravariant class here, contravariant list, are defined with a type parameter with a little minus sign before it. So if I say contravariant list of -a, that means it's a contravariant list. And the way that you would use a contravariant list is to say val, let's call this contravariant list, which is of type, and this time I'm going to use the derived class here, so contravariant list of cat here, equals, and on the right hand side I'm going to put in a new contravariant list of animal. Now look at the type relationships. If you take a look at the covariant version, the first one, we can replace a list of animals with a list of cats because cats are animals, right? In the contravariant case, I'm replacing a list of cats with a list of animals, even though cat is a subtype of animal, so the relationship is exactly opposite. And it doesn't really make sense. How can you replace a list of cats with a list of animals? Because animals can also be dogs and dinosaurs and all that kind of stuff. So it's not intuitive, at least not for lists. But watch what happens. Let's say instead of a covariant list, I actually create a class called trainer, which basically trains animals. So I'm going to replace these with this new class. And instead of a covariant list, I'm going to name this value trainer. Now, the semantics of it will change this time, because if I say that I want a trainer of cat, but I'm supplying a trainer of animal, this guy on the right-hand side is better because it's a trainer of animal, so it can also train a cat, it can also train a dog, it can also train a dinosaur, and in particular, it trains a cat, which is what I want. So I can use a trainer of animal to be a trainer of cat, which is more particular. So these are the basic variance options that we have. We have covariance, we have invariance, which means every type is in its own world, and we have contravariance, which is the opposite relation to covariance. Good. Now let's talk about bounded types. Bounded types allow you to use your generic classes only for certain types that are either a subclass of a different type or a superclass of a different type. Let me show you what I mean. So let's say I define, for example, a class cage, which can also only hold an animal. So in between square brackets, I'm going to write a type parameter a, and I'm going to add a restriction in the form of less colon, so this is an operator, and I'm going to put in the animal type here. So basically I'm saying class cage only accepts type parameters a, which are subtypes of animal. So this is how you read this generic type definition. And let's say this class receives a parameter, let's say animal, which is of type A. All right. And if I declare a value called cage, I can actually use the cage generic class to put in a dog. Say new dog. Okay, so this expression evaluates to something which is an animal. So this is an acceptable type for the cage. If I define a class car, for example, I can't write val new cage equals new cage of a new car. That's because car does not subclass animal. So even though IntelliJ has not underlined my code in red, I won't be able to run this because a new car does not conform to the expected type. So let's prove this. So if I right click and run, of course I get a compiler error saying inferred type arguments do not conform to class cage's type parameter bounds. All right. So this is bounded types, and this is an upper bounded type in animal. We have lower bounded types as well. And the lower bounded type sign is, instead of less than colon, we have greater than colon. And this is saying that cage only accepts something which is a supertype of animal. All right. So I'm going to leave the subtype here for now. Now, bounded types solve a variance problem, which is very, very annoying when we want to write covariant collections. So let's go to our little myList, and let's just say that myList is covariant in the type A. So lists should, in theory, be covariant. Now, a natural method to add in a myList type would be an add method. So if I try to add an add method, which receives an element of type A and returns a myList of type A, and let's just provide an empty implementation for now because we don't really care about the implementation. I want to show you that this function signature, this method signature, does not work even though myList is covariant and it's generic. And the error that the compiler tells me is covariant type A occurs in contravariant position in type A of value element. And you might be wondering, what the hell is that? Now, this cryptic error that the compiler threw in our face is actually the technical version of the hard question that we asked in version 1 here when we talked about covariant lists. So, if we want to define a covariant list, we need to be able to answer this question, which is, if I have a list of animals, which in fact is a list of cats, what if I add a new dog to it? Well, the answer is that if to a list of cats I add a new dog, that will turn this new list into a list of animals, basically, right? Because I have cats and then a dog, which makes the whole list a list of generic animals, right? So adding a dog to a list of cats would actually turn it into something more generic. So a list of cats, by adding a new dog to it, will turn it into a list of animals. Now, the technical implementation of this into the add method right over here is something like the following, and I want you to be very careful about what I'm about to write. So the add method will take another parameter, another type parameter, type B, which will be a supertype of A, and the element here will have the type B instead, not A, and at the end, we'll return a mylist of B. So what this says is that if to a list of A, I put in a B, which is a supertype of A, then this list will turn into a mylist of B, not into my mylist of A. So in the example with cats and dogs, let's just say that A equals cat. So I have a list of cats, and then I add a dog. So B is a dog, which in particular is an animal. Alright, so B is basically an animal. If I add an animal to a list of cats, then that will turn into my list of animals because there are cats and dogs now. So this is how we technically solve this hard question. The answer to the hard question is we return a list of animals. And the technical transcription of this is this method definition. So add with a new type parameter B, which is a supertype of A. The parameter is of type B, and the type result is also a type B. Now, I want you to not stress too much on this hard problem. This is an advanced topic, and we're going to discuss type system mastery in the advanced course. But this is an important problem to solve, and I wanted to give you a solution because we do want covariant collections. So don't stress too much, but this is a small taste of the variance problems that you get into when designing generic frameworks. Cool, now as an exercise, I want you to go ahead and expand my list to be generic. This is the only exercise that I'm going to ask of you in this lecture, and I actually want you to do it, or at least do it with me in the solution, because we'll expand the list as we go. So pause the video now and try to do the exercise. Alright, I'm in the MyList class, and let's make this generic and covariant. So, first thing that I'm going to do is add a covariant type parameter, which will start to break a lot of things. Especially if I start to replace the int type with the A type. So my list will now hold elements of type A. So the head will be a type A, tail will be a mylist of A, is empty is still going to be a boolean, add is going to receive a type parameter A, which will break our method signature, and print elements into string are going to stay the same. But now let's modify the signature for the add method, and as we've learned, we need a supertype of A. So the type parameter B, which is a supertype of A, element is of type B, and the return type is a mylist of B. So this is the abstract class that we're going to implement in empty and cons. Now let's start with cons because it's a little bit easier to think about. So my list is covariant, so that means cons must be covariant as well. So cons plus A, the head instead of int we'll make it an A, and the tail is a mylist of A. And finally extends mylist of A. All right, head and tails are going to be changed. So head will return an A, and the tail will be my list of A. The implementations are still the same. Now, the add method, of course, needs the new type parameter B, which is a super type of A. The element is of type B, and the result is my list of B. And the implementation is going to stay the same. So basically, cons is done. The interesting thing now happens with empty. So let's think about this. Empty should be a proper replacement of my list of anything. Let's just delete this code. And let me show you what I mean. So if I say a val list of integers, which is my list of int, I should be able to say empty here. But I should also be able to say empty if I have a list of something else. So say list of strings, which is also my list of string this time around. And I should also be able to say that empty is a proper value for an empty list of strings. So how do we do that? Well, my list is covariant, right? We added the little plus sign. Now, if you remember, the nothing type is a proper substitute for any type. So if you say, for example, this guy says it returns an int, but instead it returns nothing. Nothing is a proper substitute for any type. In much the same way as nothing is a proper substitute for any type, the object empty here should be a proper substitute of my list of any type. So a natural way to think about it is to make empty extend list of nothing. So right now, we need to supply the proper method implementations here and to change the types. So the head and tail should return nothing and my list of nothing respectively. Okay, the expressions will still hold. All right, isEmpty will be unchanged, and the add method will need a type parameter b. So the type parameter b this time will be a super type of nothing, not of a, because this nothing type is concrete this time. It's not a generic type. Okay, so b should be a super type of nothing, which in this particular case is always true. And the element is of type b, and the result is a my list of type b. And the implementation is going to be unchanged, because a new cons of element in empty will return a new cons of b, which is a my list of b. All right, so everything seems to match. Now let's test our code to make sure it runs well. So instead of a list of integers, let's just say new cons of 1 and new cons with 2 and new cons of 3 and empty. And a list of strings, let's just say we have new cons with a string hello and new cons with the word Scala and empty. Okay, so this is now a list of integers and a list of strings. All right. Now, if we print line the list of integers dot toString and print line list of strings dot toString, then that should print the list 1, 2, 3 and the list hello Scala. Oh. The code does not compile because I have this little cage problem. Let's just delete this or comment this out and say generic type needs proper bounded type. All right, so back to list. Let's click and run. And yes, I see the strings 1, 2, 3. The string 1, 2, 3 and the string hello Scala. All right, so our lists work well. This is how you genericize an API or a framework. This is quite a bit of work and needs some careful thinking. All right, so let's wrap this up. You've learned how to use generics, which are a method to use the same code on potentially unrelated types. So the way that you declare a generic is to define a type parameter in between square brackets. This works for classes and for traits. You've also learned how to use generic methods, which means adding a type parameter in between square brackets at the method definition which allows you to use the type parameter for the rest of the method signature. You've also learned that you can define types with multiple type parameters. And you can name type parameters with whatever you want. Usually in practice we use single letters. You've also learned an important problem in type systems, which is the variance problem, which basically says that if B extends A, should list of B extend list of A? And you've learned the three possible options: covariance, invariance, and contravariance. And you've learned about when we use each. You've learned about bounded types, which is defined by this little funky symbol less than or equal. This is for upper bounds. There is a symmetrical sign for lower bounded types as well. And you've also tested the pain in defining generic methods with an annoying variance problem that we solve with bounded types. Alright, hard topic, but I hope you found this video useful. I'm Daniel, and I can't wait to see you in the next video.